Welcome to the fourth video in our Random Forest series. In this video, we're going to build a random forest model with out-of-bag or OOB support from scratch. In the previous video, we introduced the concept of out-of-bag samples. We learned how to compute the OOB score and also derive the theoretical probability of a sample being out of bag. Now we're going to build on that knowledge and implement an OOB-enabled random forest step by step. Earlier in this series, we implemented random forests in 3 different ways. In this video, we'll extend those implementations by adding OOB support. All right, let's get started. First, we'll implement a random forest with OOB support using scikit-learn's DecisionTreeClassifier. Let's begin by importing DecisionTreeClassifier from scikit-learn. We'll use the preprocessed Titanic dataset for this example. Let's load the dataset. This is what the dataset looks like. Next, we'll define our features and target variable. The survived column will be our target variable, and all the remaining columns will be used as input features. Next, let's split the data into training and test sets. Let n denote the number of training samples. We'll use 100 decision trees, and we'll limit the maximum depth of each tree to 3. Next, let's define a function that performs majority voting across predictions from multiple trees. The input variable p is a 2-dimensional array. Each row represents a data sample, and each column contains the prediction made by one tree. Our goal is to find the majority class for each row. The predictions may contain NaN values. This happens when a sample has not yet received an in-bag or OOB prediction. We'll process each row one at a time, remove any NaN values, and then perform majority voting to determine the final class. If a row becomes empty after removing NaN values, there is no majority class available yet. In that case, we'll assign a value of -1. The resulting majority classes will be stored in the PREDS list. Now we're ready to implement our custom random forest model. First, let's create a list that will store all of the individual decision trees. Next, let's create 2 lists to store the errors measured on the in-bag and out-of-bag samples. We'll also create 2 arrays to store predictions for the in-bag and OOB samples. Each array has n rows and n estimators columns, where n is the number of training samples and n estimators is the number of trees. Later, these arrays will be passed to the majority vote function. Initially, all elements are set to NaN. Now let's start building and training the individual decision trees. We'll repeat the following process 100 times, creating 1 tree in each iteration. The first step is row-wise subsampling. From the n training samples, we randomly draw n samples with replacement. The sampled data, X sample and Y sample, form the bootstrap sample. Next, we create an individual tree using DecisionTreeClassifier. We set the maximum depth to 3, and for max features, we use the square root of the number of features. Now we train the tree using the bootstrap sample and store the trained model in the trees list. Next, let's compute the out-of-bag error. First, we identify the indices of the in-bag and out-of-bag samples from the bootstrap sample. The list bag IDX contains the indices of the bootstrap samples. These correspond to the in-bag samples. The list OOB IDX contains the indices of samples that are not selected during bootstrap sampling. These correspond to the out-of-bag samples. Next, we use the trained tree to generate predictions for the entire training dataset. Among these predictions, those corresponding to in-bag samples are stored in the bag pred array, while those corresponding to OOB samples are stored in the OOB pred array. For example, the bag pred and OOB pred arrays look like this. The first column in each array contains predictions generated by tree 1. In the bag pred array, tree 1 generated predictions for samples 2, 4, and 5. These samples belong to the bootstrap sample, so they are in-bag samples. In the OOB pred array, tree 1 generated predictions for samples 1 and 3. These samples are not selected during bootstrap sampling, so they are out-of-bag samples. Next, we perform majority voting across the predictions stored in each row of these arrays. This gives us the in-bag and OOB predictions for each training sample. For example, in this table, the majority class for the first sample is 0. The majority class for the second sample is 1. The resulting predictions are stored in Y-bag. Now let's look at the OOB predictions. In this table, the majority class for the first sample is 0. And the majority class for the second sample is 1. The resulting predictions are stored in YOOB. Next, we compute the in-bag and OOB errors. During the early iterations, only a few trees have been created, so majority voting may not work properly for every sample. For example, after the second iteration, only 2 trees are available. Consider OOB sample 4. In this example, neither of the first 2 trees generated an OOB prediction for this sample. In that case, the majority vote function assigns a value of -1 to that sample. As a result, both Y-bag and YOB may contain -1 values. To handle this, we create a mask. Cells containing -1 are marked as false, while cells containing valid predictions are marked as true. We then compare the valid predictions with the true labels in ytrain and compute the errors. The variable bag error represents the error measured on the in-bag samples. Similarly, OOB represents the error measured on the out-of-bag samples. As we continue adding trees to the ensemble, we store these error values at each iteration. This allows us to track how the in-bag error and OOB error evolve during training. Once training is complete, we can visualize these errors and examine their behavior. Next, let's evaluate the model on the test set. First, we create an array to store the predictions and initialize it with zeros. We then pass the test data through each individual tree and collect the predictions. Next, we perform majority voting across the predictions from all the trees. We then compare the predictions with the true labels and compute the test accuracy. We then display the test accuracy along with the final OOB error. Finally, let's calculate the OOB ratio. In this example, 2 out of the 5 samples are OOB samples for the first tree. So the OOB ratio is 2/5. For the third tree, the OOB ratio is 3/5. The average of these ratios gives us the overall OOB ratio. Therefore, we can compute it as follows. As we discussed in the previous video, the theoretical OOB probability is 0.3679. We'll check whether the measured OOB ratio is close to this theoretical value. Next, let's use scikit-learn's RandomForestClassifier. To enable OOB evaluation, we simply set OOB score to true. We train the model using the training data and then generate predictions for the test data. Next, we compute the test accuracy and examine the final OOB error. We can compute the OOB error as 1 minus the OOB score. Now let's take a look at the results. As more trees are added to the forest, both the in-bag error and the OOB error gradually decrease. With the DecisionTreeClassifier-based implementation, the test accuracy is 0.8027. The final OOB error is 0.1781. And the measured OOB ratio is 0.3674. The theoretical OOB probability is 0.3679, so the measured value is very close to the theoretical result. Next, let's compare this with scikit-learn's RandomForestClassifier. The results are shown here. Now, let's run this code. We get the following results. Now let's move on to implementing a random forest with OOB from scratch. Earlier in this series, we built a random forest classifier from scratch. In this section, we'll extend that implementation by adding OOB support. We'll modify the MyRandomForestClassifier class that we created previously. First, we add a new input parameter called OOB error. If this parameter is set to true, the model will compute the OOB error during training. If it is set to false, the class behaves exactly like the previous implementation. Next, we add the majority vote method that we defined in an earlier slide. Then, in the fit method, if OOB error is set to true, we compute the OOB error using the same procedure we just discussed. The rest of the code remains unchanged from our previous implementation. When OOB error is set to true, it returns the in-bag and OOB errors measured during training. It also returns the OOB predictions. Now let's use this class to build a random forest model with OOB support. First, we load the Titanic dataset and create the training and test sets. Next, we create a random forest model using MyRandomForestClassifier. Here, we set the OOB error parameter to true. We then train the model using the training data. The dictionary H contains the in-bag and OOB errors collected during training. Next, we visualize both the in-bag error and the OOB error. We then generate predictions for the test set and compute the test accuracy. Now let's look at the results. As more trees are added to the forest, both the in-bag error and the OOB error gradually decrease. With this implementation, the test accuracy is 0.8341 and the final OOB error is 0.1886. Now let's run this code. We get the following results. In this video, we implemented a random forest model with out-of-bag support from scratch. In the next video, we'll explore missing value imputation using the proximity matrix.